Today we're going to see, I always say it's an interesting topic because I always like talking to you and getting you excited about learning more things about systems, dynamics, and the response of system. In this occasion, you see, we have a little system in there that you have seen before, and I'm going to take it over from the point that we had the equations of the system and we had the transfer function of the system as to what to do with it. And let me just go here. What we have done in the past, and I will very quickly do it here, is we said that if you make a free body diagram of this, you can actually derive the equations that control the system by writing the forces that apply on this mass, right? And so if you write it down, the equations of motion for this are going to be that F minus K times X minus B times X dot is going to be equal to M times X double dot. Yeah? What we, if we rearrange this, because we would like to apply the Laplace transform and collect terms to find a transfer function between the value of x and f. Then let's put it this way, and then applying the Laplace transform, we will have that ms squared times x of s plus b times s times x of s plus k times x of s, like that, equal to f sub s. And if we have this, we can actually write this like ms squared plus bs plus k, and then this is times x of s, like this. And you can write the transfer function that x of s in relationship to the input is going to be equals to 1 over ms squared plus bs plus k. So I would like to study this system and the response of the system so that we can actually reach some conclusions as to what will happen if the values of m, b, and k are different. So for example, in this case, I'm going to say that m is equal to 2, that b is equal to 10, and that k in this case is equal to 200. Yeah. So I am going to say that the transfer function, we could call it g of s, which is in reality x of s over f of s, is in fact 1 over 2s squared plus bs plus k. Plus, no, what am I doing? I need to put the numbers. That's what I was doing. So we don't want symbols anymore. So this is, over here is 1 plus, this would be 10 s plus 200. So let's examine what happens if we go to MATLAB and we ask, I would like to put a step input to the system, and let's see what other conclusions can we reach from it, because in here what we are doing is we are going to plot the response of this, and one of the questions that I want to raise in here is how these coefficients influence the response. Now, you know that if you set this denominator to 0 and find the value of s, that values of s, that are the solution of this so-called characteristic equation, say something about the system, and in fact it reveals a lot about how it responds. So let's just while we're waiting for MATLAB to come up, you can say that we can find out what the values of s are. But since MATLAB is already awake, I'm just going to say, I'm going to enter the transfer function. Because the numerator is going to be 1, which is there, and the denominator is going to be equal to what we have in here is 2 is a square, and then we have a 10, and then we have a 200. So we enter this as a denominator with the polynomial coefficients, and we calculate the transfer function in so that to enter what we have in here, numerator and the denominator, and if we enter this, we get the transfer function. You see, the transfer function is here, just as is here. But at this point, once MATLAB knows the transfer function of this little system, we can make some tests. Like, for example, say, find me the step response of the system by entering this command. Step g is the transfer function, and the computer is going to do this calculation for me. So we will see. It's going to take a little bit. There it is. So this is the response of the system with the value, this coefficients here. Okay. Now, if we were to find out the roots of the characteristic equation here, because we would like to know, as the title says, the roots of the characteristic equation and how the system responds, keep in mind it's like this with the values we gave it. Okay, so can we calculate the solution of this equation? Because we can do it with MATLAB, but also we can do it by hand. Just to illustrate my point, I am going to do it by hand first, and then we'll use MATLAB, okay? So in here, you can say S1 and S2 are going to be equal to minus 10 plus or minus the square root of, let's see, 100 squared minus 4 times 2 times 200, and then this is going to be divided by 2a, which is 2 times 2 is 4. Alright, so what values do we have? S1 is equal to minus 10 plus, this is 100, the square root of minus 1500 divided by 4. So this is, see if we can do this, minus 10 plus the square root of, no, not the square root, we figured out what it is now, and we write it down, and the value is approximately 38. So we will put this in here. This is minus 10 plus this The square root of minus 1500 is 38.3, I believe, times I. And the other one is 2, is going to be minus 10 plus the square root of minus 1500 and then divided by 4. And this is equal to minus 10 minus 38.3i. And of course, we need to divide this by 4. See? I want to reach one important conclusion here. With the values of this with the values of this function here, I can actually make a plot in the complex plane where this is the real axis and this is the imaginary axis. Okay, where in this plane are these roots? See, minus 10, divided by 2 would be minus 5, someplace in here, and then plus 38, so that would be something like this, yeah? And the other one would be the same, but the complex conjugate pair. So that is, in here you have S1 over here, and you have S2 over here. So what I'm trying to say is, if the roots are here on the left-hand side, we have obtained this response. See? The question is, if I play with the coefficients now, can I change the way the system behaves? And I could change it in several ways that will really affect the system. For example, I could, because it's a second order system and we know the physical system in here, the way it is. Let's see, this, so that we don't lose what we're doing is the body was like that. We know the system. We know that if we change, for example, the value of b, and we increase the value of b, what will happen? So let's go to MATLAB and say, okay, I am going to redefine my denominator, and instead of b and 10, I will make it b to be 60. And I redefine my transfer function and define what g is. And then I said, why don't you find me the step input for this? And my response is going to be like that. See, look, very different. We don't have any oscillation basically. And then the damping increase. The response of the system is very different. And the roots of this characteristic equation now correspond to this answer. So what I'm trying to say is, depending on where these roots are, that's where we will find this. MATLAB has a way to find the roots. Let me see. I believe this, maybe this will work. Yeah, it does. So you see the roots of the denominator in this case are at minus 26 and minus 3. In fact, you know what it did? If you plot this in the complex plane, what we use to plot things in the complex plane is the root locus, our locus of this g. You see, both of them don't have imaginary values right now. They are on the axis. This would reveal this if once we plot this in here. You see, there it is. This one is the value here, and this is the other one. Okay? So let's just look at, you know, how the relationship of where the roots are affects the system. That's what we're doing. So now let's say instead of 60, I am going to say, no, no, I don't like that. I'm just going to make it smaller and see what happens. Like instead of a 10, I do a 2. Yeah. So redefine the transfer function. And now I get the response of the system to a step input in here. Let me just close the old values here. But we go here and we say, okay, find me the answer. Wow, you see, I lower the damping and we have lots more oscillations on this. But when this happens, where are my roots? I could just say roots of the denominator that we are doing. Wow, these are complex conjugates. So you see, this corresponds to this plot that I have. So what we have concluded here, and I'm going to do a drawing over here to draw, I'll do it with red. Okay, the response of the system, if the roots are here, calls for this kind of answer. Huh? Now this is this one over here, the same. So like this. Yeah, very good. Now I am going to do something else. I am going to make it in such a way that the roots are on the imaginary axis. Oh, you know, let's not waste our time, but to say that the previous one, when the roots were there, the system response was basically like that. No oscillations like that. Yeah. But now, what would happen if I place the roots right here? What do you think will happen? If I place the roots over there, we are going to get oscillations forever because it means that there's no damping. So what I'm going to do is I will go over here to MATLAB and say, listen, if there's no damping, what I have in fact in here in this is a 0, right? Like that. And if I do that for the denominator that this is 0, and I calculate my transfer function, this is what I get. And if I produce the response, remember it was like that, but now if I do the step response to this, look what happens. So we conclude that we have oscillations forever if the roots are over here. So let me just add this to the drawing over here. And so what we are reaching the conclusion is that by knowing where these roots are, we can tell something about how the system behaves. There we go, like that. Now that we have done all these tests, I am going to yet do a different test. I am going to go and say, okay, look, instead of doing this, I am going to, this was a 10, right, originally, but I am going to do a minus 10. Oh, before I do this, on this transfer function that I have, let me just delete this. Find the roots. Where are these roots? These roots of G, right? Let's see what G is this. Not root, it's root. I believe, right? I think this is what we did before, right? Step. Oh, I think I did the R locus. No, but I believe we can find the roots of this. Let's give it a try again. I think this is just the syntax. Maybe not. R locus of G. Then there they are. See, the roots are on the imaginary axis. But I was proposing here that I am going to still play with this a little more and say instead of this being a 0, I'm just going to do a change of sign and see what happens. So I do a change of sign, and then oh, I know what I did wrong. This is what I was doing, see. Now guess what? The roots are on the right hand side of the plane because it's 2 plus 9 and 2 minus 9. So those roots are going to be on this side, see, on this right here. Someplace in here and the other one over here. Now what's going to happen with the response if the roots go to the right hand side? That is the question right now. So we go to MATLAB and we say, okay, I like to find it out. Would you please give me the step response to this and see what happens? And look what happens. We have a very bad response. You know, the things, let's see, let me make sure that we are correct. Still, this is the transfer function. Okay, sorry, I didn't do the change that. Yeah, this is the denominator, but I still needed to redefine the transfer function, and I didn't do that. Sorry, because we got the same plot. I said no, that can be. So there's the transfer function, as we see here with the minus sign, and we said, you know, we saw the roots in there. I'm going to say, tell me what the step response of this is. Wow, look what happened. It goes over here and then right above 4, so it blows up. So instead of damping the motion, anything that is on the right hand side of the plane would cause a problem. So if you have it over here, it means it goes like this, and then all of a sudden, boom. And same thing over here, you know, it starts nicely, responds, and then all of a sudden you have this. See, that's what it is. So in conclusion, and based on the topic that we have at hand here, the roots of the characteristic equation and the system response. It means that if you have the roots right here on the real axis, no damping, and the system just basically has no oscillations. If the roots are complex conjugates, most normal systems will have some damping and vibrations will cease. If you are on the imaginary axis, oscillations forever. And if you are on the right hand side, you have lost hope. By then your system is messed up because the system now has roots on the right hand side, and the response of the system shows that the system will actually basically, instead of damping the response, will create a major problem. So that is the conclusion that we can reach here is the location of the roots have everything to do how the system responds. The other conclusion that we can reach is that if you have a negative sign on the denominator, this should be a flashing red light for you to tell you that there is something wrong with this picture. Like, no matter where it is in one or the other, for example, I could just make the negative sign over here or on this one over here. You know, if we try it on here and we say, okay, this is the denominator, and I do the transfer function, see there's the minus sign there, and then I want to know what the response is going to be. This is the transfer function, and you say, okay, find me the step response to this. Wow, look at that. It goes over here like this to this, and then boom, blows up. So this is not good. When you have the roots on the right hand side, terrible problems. Let's give it a try as a last experiment that we're doing right here, and MATLAB is helping us to put it on the first term on the negative sign. I believe that would also would give us problems. We need to do the transfer function like that. Oh, yeah. So we've got the transfer functions there, and then we need to get the step response of this transfer function, which is going to be like this. This too is bad. This one blows up, but it goes down instead of up. Nevertheless, I think I would have hopefully convinced you that roots on this side are bad news, and convince you also that roots on the left are okay. No, normal systems work like that. But any one over here is on the borderline, and any one on the right hand side is a lost cause. So this is how we can illustrate how the system responds when you have the roots in different places. Now, of course, you can take it one step further and say, well, knowing the transfer function, if I build a unity feedback loop to the system and I change the value of some parameter there to test the system, I should be able to plot the location of the roots on that. So that is called, it is the famous root locus plot, which we can actually experiment. And well, let me show you what it is. I think we can very briefly uh, write a little system in here where we have the original system here, and you have a response in here, and you feed it back with a unity feedback, and you say this is your transfer function, and this is the value of a constant k. Professor Evans in the 1940s, he's a professor at the University of Pennsylvania, came up with this little test that he says that if you know the transfer function and you can change the value of k on this loop, you can trace all the values of the roots, and therefore you could also predict whether the system will go unstable. So what he did is he changed the value of k from 0 to infinity, and MATLAB has that tool built in. So like for example in here we have this, we know the roots are on the right hand side, but just so that you can see our locus, root locus of the transfer function g tells us, see here where they are. This is on the right hand side, this is over here. Okay, but it just as if we put the transfer function and we add, let's say, one more term, we make it like a third order system like this. The transfer function obviously is going to have a difference. See, there's a new transfer function, and then we will have the root locus of this is going to be very different. You see, it has 3 roots now, 2 on the right hand side, 1 on the left. This system would be bad news. In fact, so that you can see it, I am going to define the different figure 2, let's say, in there, so that we see it on different figure. And on this one, I'm going to ask for the step response of my using my transfer function, and look what I just got. This roots here verify that my system will be bad response, unstable, it will blow up. But if we do the fixing of this thing, and we can bring it back, to the other side, then obviously this might be different, and the response would be normal, as we have seen at the very beginning of this lecture. But with the roots on the right hand side, this is what happens.